So thank you very much. So we are back to the second talk today, and we are very happy to have Vlad Margarint, so sorry for the pronunciation, who is telling us about a bridge, bridges between random matrix theory and the Schramm-Loewner evolutions. So please.
Yeah. Thank you very much for the invitation. Thank you very much for having me here. So as I said, this talk was made possible by several people. Some of them are online, Matteo D'Achille and Claudia Rella and Veronica that is here in the audience, and Emmanuel that helped with this. So I would like to thank everybody first before I proceed. So my name is Vlad Margarint. I'm currently a tenure track assistant professor at the University of North Carolina at Charlotte. So this is one of the urban places of the UNC system, is in the city of Charlotte, is on the east coast of the United States. This year it became an R1 university, so we are very happy about this. It's a major jump for this. What I'm going to tell you today is a bridge between random matrix theory and Schramm-Loewner evolution. Before I proceed, though, I'd like to tell you a bit about myself, as I'm, let's say, an early career researcher. So I started myself to work on random matrix theory. I started to work on random matrix theory when I was a master's student, but then I moved to the SLE part. So I'm less knowledgeable in the random matrix theory part because I started there, but I moved a bit. Now I'm moving back to combine the two. So I'm going to tell you today about how this can be, how you can build a bridge between these two. I'm going to focus the presentation on the Schramm-Loewner evolution side. So for the people in the audience, because I recognize some experts here that are indeed very knowledgeable in this area, you can just skip this part, but it's designed to talk like that for the people in random metrics to get a glimpse from this other part. So I'm going to start with the Schramm-Loewner evolution part, or the main part of the talk, a short introduction and the main ideas, and then go to the random. Right, so what is the main idea here in the back? So I'm having this object in the picture that is a sample of what I call a planar loop erased random walk, an object that was, to the best of my knowledge, introduced by Professor Greg Lohner from University of Chicago. So what is here in this image, you're going to see a sample of a random walk on the Z2 lattice. This is basically made from two colors, from the red and from the gray. You see, because you start from a vertex, you have equal chance to go to the neighbors, and you, of course, can create loops, right? So you see this sample of a simple random walk, first in the plane, from which I remove the gray part. The gray part are the loops that this object has made in chronological order. Naturally, when I'm having this removal procedure, I'm remaining with the red part. The red part is, by its very own definition, is a simple object. It's a simple curve because I remove the curves, the loops chronologically. Okay? So I have the main idea now is that was introduced by Schramm in the 2000s was to try to give meaning to the scaling limit of this loop erased random walk and other planar statistical physics models. So what is the scaling limit? You can imagine that right now I'm looking at the object at a fixed lattice scale, let's say delta Z2 with some parameter delta. If I take that parameter delta to 0, that is, if I zoom out from this object, what do I see? What can I describe the scaling limit? Can I describe the limiting curve? As you can see, by its very nature of this model, this curve should be simple. Should be simple because I removed its intersections by the construction. So we're going to arrive at this a bit later. So as I said, I'm going to focus first on the basics of the SLE. So people that are experts on this, I'm going to excuse myself again, but then I'm going to go to the bridge with the random metrics. This is going to be in the second part. So okay. Yeah, so what is the idea now? The idea that was introduced by Schramm again was like, well, I want to give meaning to that red curve, the scaling limit of the loop erased random walk, let's say. And for this, I'm going to start with the following picture. I'm going to start here with the upper half plane. Here is on the left is the upper half plane, from which I remove this curve, gamma 0t. I basically cut this defect, let's say, in the upper half plane. And I have gamma 0t. This is a time between 0 and t. I just fix some time t. I have now obtained in the left part of the picture, I have a simply connected domain. that is the complement of this curve. So the complement of this curve in the upper half plane that I'm not sure if okay, this part here is a simply connected domain. And I have from Riemann mapping theorem a three parameter family of maps that moves conformally this upper half plane with the curve removed back to the canonical domain that is the upper half plane. And so I got this, let's say, green point here, that is the tip of the curve, this part here, is going to be moved somewhere on the axis. This is UT, I just call GT of gamma T. As you can see, I index this three parameter family of maps with T, because for each time I have this type of maps. And I hope you can see this text up. Now, the Loewner equation encodes the dependence between the evolution of the maps GT when the curve gamma 0T grows. So I have right now a geometric picture. I have the upper half plane, I remove a curve, I have a conformal three parameter family of conformal maps that move back to the upper half plane. Now, this is one step forward now to build this theory is to, well, I would like to work with unique objects. I would like to work with unique maps, right? Because I want to somehow fix those three parameters. And to do so, I'm going to use the following normalization. As you can see, I'm requiring that as I approach infinity, as the modulus of this z grows to infinity, the maps looks almost like identity plus this is in the Laurent expansion is the other terms appearing. So what did I do here? As you can see, I have, first of all, I have, I fixed the fact that the term in the front of z is 1, right? So this is the coefficient belonging to the z part is 1. So I did a choice there. Is real and so on. And then I take B0 to B0 in order to fix another type of parameter. Now, the coefficient B1, the one that remains further in this expansion, this depends on time. Because I remind you, this curve grows, these maps depend on time. In particular, this coefficient B1 of B1 is a function of time. It can be proved that B1, that is called the half-plane capacity of this curve gamma T, is additive, is continuous, and is increasing function. So it's a function of one parameter that is additive, continuous, and increasing. So one can reparameterize it to be just 2T. This is a choice of this type of function. And so basically, I'm working with this type of maps, GT of Z, that are Z plus 2T over Z plus further terms. And this map satisfies the Loewner differential equation, where this 2 appears. This 2 here, the fact that I have this 2 is linked also with this type of 2 thing. Sorry. Yeah.
Just a question, but so this map is the initial map.
Yeah.
Is fixed by what?
So it's basically the existence theorem of the Riemann mapping theorem. You have a simply connected domain, and you have another simply connected domain, and we know that there are 3 parameter family of conformal maps between them by the Riemann mapping theorem.
So that's a conformal transformation.
It is a conformal transformation. I fix it further, I fix those parameters further by imposing certain behavior of these maps at infinity. Essentially, this is one way.
But how is it connected to, for example, so this is some just analytic conformal, like local conformal transformation.
This is basically you have is connected with the fact that here you have already designed a simply connected domain that is depending on this curve gamma T now. And here you have another choice of a simply connected domain that is canonical, that is the upper half. So you have these maps between them.
So not any analytic or holomorphic or anti-holomorphic function works.
No, they depend on this choice of the curve.
Okay.
Yeah, this is and these maps satisfy the dynamics, the Loewner differential equation. That is here. I mean, I'm going to come back to this object here. You can think about this as an evolution in the family, as an ODE in the family of the conformal maps, if you want, in the family of functions of this stuff. And the UT for now, I'm going to come back to this a bit later, it is a real valued function, is real value for me. I want to tell you a bit before I move on that the theory is a bit more general. So as you saw, I did the other half from which I removed the curve, but you can also remove, I hope I'm writing big enough, you can also remove a half. a bigger set, if you want. This is, as I say here, as a compact hull, is a compact set with simply connected complement. So I need a simply connected complement coming back to the question here. And I got to note this. So I'm basically having this K. I have this corresponding conformal map GK that I evaluate on the exterior of that. And I'm moving back to the upper half plane. And of course, this is the static version. If you want, I can also put the time. This has to grow on time. I have right now GK that depends on time. So I basically have a family of halves that increases on time now, right? And I have for each one a conformal transformation back from this simply connected domain that is the complement of the hull that I just called there HT. This is a typical notation that you're going to see in the theory. And I will have this family of maps back to the upper hull. Now, this cause for which the framework of the theory functions is they have what is called the local growth property. So let's clarify a bit what is the local growth. So if this is KT, what do I mean by the local growth if I follow that definition? First, I need to introduce what is called the radius of the hull K. That is the infimum R, such that the hull is basically surrounded by a semicircle fixed at some x, right? So it's a geometric notion that tells me, well, K is included in RD plus X. D is the unit circle, I scale it by a factor R, and I'm picking some X such that I'm surrounding this hull, okay? And now I want this family of hulls, for which the theory still functions, to be what is called increasing with the local growth property. So what do I mean by that? So I have this, let's say this is KS, and this is KT, is the next one up to here. And the difference between KT and KS, so the difference, this is KS, this is KT, is this whole new part. This is the upper hull plane. The difference between them is this one. So this is, as you can see, this is the difference between KT and KS. This is the difference between the two hulls. And now, if I remove this with the mapping corresponding to the KS hull, so this is exactly this, the map that removes conformally this defect back. So for this map, this additional piece here is just a part of the simply connected domain where I can apply it. And it's basically going to need removed here somewhere, such that this KST, that is this image, this KST is basically is controlled by this geometric notion, in the sense that the radii, if I want to get a semicircle that surrounds this, the radii of this KT plus H should go to 0 as H goes to 0. It's exactly what we believe to be local growth. Okay, it's a geometric way to say that this is locally growth. So this is that basically this is in a bit more general how this thing works. Now, Loewner equation.
So for instance, it's correct Loewner equation because you have function x of time, yeah.
Yes.
Consistent, yeah. It's
Yes.
really some extra term.
Yes, exactly. Yes, thank you. Yeah. So in 2000, as I said in the beginning of the story, we were trying. Schramm was trying to give meaning to the scaling limit of the loop erase random walk and other planar statistical physics model interfaces of those. And now, basically, first of all, these are coming from statistical physics. So there are some random interfaces. There are some random curves, right? So in order for this machinery, you saw this machinery is basically taking for now the deterministic curve, is looking at a simply connected complement, and is having the correct family of conformal maps to remove it back. But I need to describe a limiting object from statistical physics now. That is random. So I need random curves. Essentially, in order for this to output random continuous curves, UT has to be random continuous driver. I need the continuous and random driver. And Schramm used this idea and realized that if I really want to model, for example, the loop erase random walk that I started with, that object from the statistical physics viewpoint, it has to satisfy two conditions. First, it has to be conformally invariant, and second, it has to have what is called a domain Markov property. Domain Markov, of course, if you think about it, the loop erase random walk is not a Markov object to start with. It's not Markov because it basically, you have to remove chronologically and the path interacts with its previous component. However, there is a domain Markov. There is, in some sense, a Markovianity in the geometry of the domain. What do I mean by this? If I have the upper half plane and I see a bit of the loop erased random walk, let's say I just run the object up to some time, the remaining part from that time onwards is still a loop erased random walk, but in the new domain, that is the previous domain from which I remove this first part of the curve. So it's in some sense a Markovianity of the geometry of this. And this property is actually very useful because combined with the conformal invariance, this tells you some information about the driver. So if I can think about the following, if I impose these two conditions, domain Markov and conformal invariance, what UT should look like? It's something random, it's some random process, but it should be able to produce this type of properties to be satisfied. So if you put these two together, you learn the following about UT. You learn that it has independent increments. First, this has to do with these pictures that I showed you, and it has the same law. So independent increments with the same law. So one candidate for this is a Brownian motion with a drift. It's a standard real Brownian motion with a drift. This can be a good object because it has independent increments, and it keeps you these properties fixed. And if you impose certain symmetry with respect to the imaginary axis, you can get rid of the drift, and this is how you arrive actually that the natural object to be considered there, if you want to capture the scaling limit, should be a square root of kappa times Brownian motion. So basically, this is a Brownian motion, is a standard real one-dimensional Brownian motion, and this is a parameter kappa that is a parameter here that it's historically done like. Okay, so essentially this leads to the following introduction of the learner ideas now. Is like this was basically the definition. Now we see the first time the definition of the SLE. So I'm going to look at the Leverner equation that is driven by this square root of kappa times Brownian motion. Again, this is a real Brownian motion. So I basically you can think about it as dynamics in the space of conformal maps given by this ODE, by this random with this random function that is a standard Brownian motion. Times a fact. So basically, this is my object to start with. Now, this was introduced by Schramm in the 2000, and now the question is, okay, I have this ODE, but remember from where we started. We started from this picture in which we had a curve up to some t, and I told you that there is conformal maps from the exterior of that curve back to the upper half. But now I say, okay, I'm looking at this ODE, and I want to recover, if I start from this perspective now, I start with this ODE in the space of conformal maps, I want to recover back the geometric picture. I basically want to use this picture to come back to the curve. How I can recover the curve here? This is the question. And this is the notion of the SLE trace there is given by this. I'm going to define the following object, the limit, when y goes to 0 plus of the inverse of this map in the following point. So let me clarify a bit what do I mean by this inverse. So GTE is a function of both prime and z, right? Here I mean the inverse in the z component. I mean the inverse in the spatial component. So how you should think about it in this picture, I'm shifting a bit the direction, and I'm taking this type of limit along this parameter y, a limit from the right, and I'm basically taking the inverse of this map, but the inverse in the space part, not in the time part, and I'm taking this limit, and I want to map using this inverse map in order to recover this object. Make sense? So it's exactly what you would do. You want to recover back the geometry, you will define it as an inverse through this limiting procedure from the right-hand side, we'll define it as a limit. But now, of course, the natural question is, does this limit exist and is continuous in time? Because in order to talk about this SLE trace, we need that this limit is almost surely exists for almost every choice of the standard Brownian motion here. So it almost surely exists and is continuous in time. So I need this to be true. This is actually non-trivial. So in order to show that this limit exists and is continuous in time for almost every realization of the Brownian motion, this is a complicated question. Because you start with this and you want to basically be able to say this is true. This was actually done by, the two papers, essentially for kappa different from 8. The main reference is the basic properties of SLE. This is done by Schramm and Stefan Rode. So this is Rode Schramm paper. It appears in Annals of Mathematics, and this is one of the instances where we can prove that for kappa different from 8, this limit P almost surely exists. And we know also for kappa equal to 8, this is resolved by Schramm-Loewner Evolutions. So we basically can talk about the existence of this object for all these parameters. And we will see a bit of the proof of this today, just for you to see how these things are done in reality. Okay, before I move on, I want to convince you that there is a PDE version of that. Basically, I call FT the inverse in this type of maps, the inverse in the parameter Z. This type of maps, if I really want to write a corresponding evolution for them, they satisfy a PDE, that is this PDE here. It's much harder to analyze in principle because you have this derivative in the Z component as well. And the nicer object is actually the inverses in time of the GT map. So the inverses in Z satisfy a PDE, the inverses in T, because there is two parameters, T and Z, the inverses in T satisfies an ODE. That's nice, because this is basically the backwards in time evolution, where this BT hat is simply B big T minus B big T minus T. It's the reverse in time of the Brownian motion. We know the statistical properties of the standard Brownian motion. So this is a nicer family of maps than this. And this is why it's in practice is nicer to work with this and relate back to this type of maps. And this is how some proofs inside this theory work. So essentially, just to say it briefly what we did, we defined this new basically random Loewner differential equation, this Schramm-Loewner evolution, as a evolution in the space of conformal maps driven by this current of kappa Brownian motion. And we said that we call the SME trace the limit when y goes to 0 plus of the inverses in Z of these maps coming from there. And the existence and continuity in time of this limit is proven. It's happening almost surely for all the parameters kappa, if you want. Okay, now how these curves look in reality, this is a simulations. We worked a bit on some algorithm to simulate these SLE traces. So this is one instance of that. So you can see it has a bit of a fractal behavior in reality coming from the Brownian component. And this is a sample of the SLE trace for kappa being equal to 8/3. This is one of the nice parameters to choose to simulate because to the best of my knowledge, there is still a conjecture, an open problem, if the limiting if the scaling unit of the self-avoiding walk, another more complicated object, converges to the SLE 8/3. So this is to the best of my knowledge still open. If people have more news on that, please let me know. So this is why we try to do this type of simulation. Okay, so this is how this object looks in reality. So it's not really looking like those smooth, nice curves read from the beginning. So I try to have a picture of that. Now, I'm going to just tell you a bit about how this Rode-Schramm convergence works, how we can basically say that this limit exists and is continuous in time almost surely. And for this, I need the following first notion, is that a continuous path generates a family of increasing halves if the complement of those halves as time increases is the unbounded component of h minus gamma t for all t. So basically, this is saying that there is a way to say that halves are generated by curves. Okay, this is a technical way if you want to say this. And what is the main, coming back to this result that I said, it is very hard to show this type of limit, the existence and continuity in time of this limit. Rode and Schramm said that for kappa different from 8, then this ft, that are these GT inverses in space that I want to take the limits of, as you can see here, extend continuously to the closed upper half plane for all t, and moreover, they are basically generate this type of house. And basically, one of the main ideas here is that you can basically talk about this limit, the existence of this limit and this continuity in time almost short, and moreover, these curves have different behavior. We're going to see in a second what do I mean by generating the how. Maybe the first question now that you have is like, why is kappa different from 8, right? This is, if I look at this statement, it's great that I can recover this object that is known, it is very hard in the beginning, but why is kappa different from 8, right? And the reason for that is basically coming from what do you need really to show this type of statement? So the statement is coming from this type of estimates that has two components. The first component is something to do, I'm going to go first to the second one because it's easier to follow, and then I'm going to go to the first. The second one is you need some control on the driver. You need some control on the driver. If you have this control on the driver, you can push through the estimates. And as you can recognize here that this is something to do with the regularity of the driver. We know that the standard one-dimensional Brownian motion is a half minus epsilon, is weakly a half holder. So it's a half minus epsilon holder. So we have this type of control. The second control is a bit more complicated now. You can see that this has to do with the following picture. I have a dyadic scale in time. So I look at a dyadic scale in time. I take a dyadic partition of time, and I take a dyadic partition of space at a different rate. As you can see, there is a 2 between these two. And I need a control. So basically, the picture is something like this. I have a dyadic partition in space here, and I'm going to the limit. I'm taking this going to y, going to the margin, to the boundary, at this type of steps. And I'm looking at the time of this form, and I want to control the derivative of these f hat maps that are simply some versions of this GT minus 1 maps. It's just a notation. This is essentially a control on this GT minus 1 maps. So what I need here is, as I'm approaching the boundary, I need to say that this derivative of this inverse maps are well behaved in this sense. So I'm taking a dyadic scale in which I'm approaching the boundary with a dyadic time scale, and I need this type of control for the maps. If this is satisfied, is essentially with this type of correction, then I get, with these two combined, I can show that this limit exists and is continuous later on in time, almost sure. So I need this two to be checked. And this is the hard part. This is a property of the driver, but this is a hard part because this requires a lot of control on the fact, on the maps themselves. And maybe now you start to think about, well, but just a minute. I mean, this is a continuous in time object. Why do I look only at first of all, only at the dyadic scale in space? I mean, I need to control it everywhere, right? And the thing is that, you know, between these points, you can use the fact that the maps are conformal. At the end of the day, they are conformal maps. So you have a distortion estimate between these points. So if you have enough control on this dyadic scale, between them, you have some properties of the maps, distortion estimates that allow you to control it. So this is essentially one of the main ideas behind this. This is a bit about the theory. So basically, we can talk about this type of object. We have the notion of the SLE trace. And now it's proved that this object has some phase transition. So these curves are up to k equal to 4. They are simple almost surely. This is the regime of the loop erased random walk that we were interested in the beginning. Actually, it was proved that it was kappa equal to 2 is the correct scaling limit here. So the loop erased belongs essentially to this type of picture, the loop erased scaling limit. From kappa between 4 and 8, we have this double points almost surely, so the curve starts to behave differently. This is why you need intuitively the notion of generating a how, if you want the one that we needed before the theorem. And now from kappa equal to 8 and bigger, you start to have this space filling behavior. So I hope I gave you a bit of a crash course on this type of SLE picture. I want to move now to the multiple SLE model and to the links with the random metrics theory. So as I said in the beginning, I started myself to work with the random matrices, but I moved to SLE and now I'm coming back to this. So what is now a multiple SLE model? A multiple SLE model, you see, before I draw a curve, I just draw one curve. A multiple SLE model, I can maybe erase here, is going to be, as the name says, multiple curves drawing from the upper half plane. So I have, especially there are many models also of this multiple SLE, as you can see there are many authors there. The list is non-exhaustive. I tried my best to capture all the literature, but I'm always looking for updates. So in case you spot someone that I didn't mention, you can tell me. So now it's a multiple SLE model. I consider this simultaneous growth. So I have lambda 1, lambda 2, and say lambda 3, and so on, up to lambda n. Let's say I have n curves. I don't draw all of them. And I have right now a GTN, a family of conformal maps, that are like before, from the upper half plane, from the complement of this n curve. So I have to take GTN. What is the correct set to be removed now? Well, I have to take the union of all these curves from I up to n of the gamma t phi. And I have to map this back to the upper half plane. So I have a map from the complement now that is a simply connected domain outside of these curves back to the upper half plane. So this map, this GTN map moves somewhere here. I remove this n curves now. The standard Brownian motion from here becomes the Dyson Brownian motion. So what is this? This is a system of interacting particle systems. Let me describe it a bit for you here. As you can see, here I have now n drivers. For each one of them, let's look at the lambda ti. I have the following thing. I have independent Brownian motions scaled by some factor n beta. Beta is linked with kappa with being, it's a simple algebraic relation between them. Beta is 8 over kappa. And basically I have n independent Brownian motions, and I have this interacting picture, this Coulomb type repulsion between the particles, scaled by the factor of 1 over n in this type of scaling. So you can think about it intuitively like this are some sort of electrons, right? Because of this Coulomb type repulsion, and they have noise, this kind of thermal noise on top of that, and they are evolving like this. So it's like electrons in a heat bath, if you want a mental picture for that. And of course, this is a model, as the name says, introduced by Dyson. It's I'm going to link it with random matrix theory there. You're going to see that there is a Olfin-Uhlenbach dynamics in the space of matrices that has exactly the eigenvalues that are given by this Dyson Brownian motion. I'm going to use this beta parameter that is, just to keep in mind, is simply 8 over kappa, just because the random matrix literature uses the beta parameter. So it's easier for me to tell you about this. One interesting thing to notice before I move on is that you will see something interesting now. Kappa 4 and 8 were the critical parameters in the SLE picture. I remind you this. At 4, the curve starts to change statistically, from simple to having double points, and at 8, from double points to space filling. So 4 and 8 are now corresponding to, if you do the simple computation, 1 and 2, or 2 and 1. 1 and 2 are the nice beta parameters, I call them nice in the random matrix theory. They are the so-called beta equal to 1 is the so-called Gaussian orthogonal ensemble case, and beta equal to 2 is the so-called Gaussian unitary ensemble case. So the thing nice here is that the critical parameters in the SLE in one of the stories is linked with the nice parameters in the random matrix theory picture. They are exactly 1 and 2. And this is, the format of this is motivated by the people who looked especially at this model. The literature that I cited before looked at variations of various models in which how you grow these curves. Specifically, I'm looking at this motivated from physics model in which the driver is shown by the work of Carvey and later on by Loewner and Vivian Healy, that this is the correct driver to be picked. So the correct change from one curve to n curves, if you want simultaneous growth, is this type of Dyson Brownian motion. So now, as I said, the continuous, the SLE that I'm looking at is this GTN now. I'm focusing on this family of maps. What are these doing? Well, they are solving a variation of the previous Loewner differential equation. There's like one in which before I had, if you want n equal to 1, I did not need to use this sum, and I did not have this scaling factor. Now I'm using this, now I have this new equation because I have n curves, in which these lambda pj's are exactly the Dyson Brownian motions. Okay? So the Brownian motion from before is now n of them, and interacting particles like Dyson Brownian motion. And I have this new object. I have a multiple SLE with simultaneous growth. Now, there are many works on this Dyson Brownian motion behavior. One of them is linked with very fast convergence to local equilibrium. I want to tell you a bit about this. Why is this an important feature? So, to the best of my knowledge, this was used in the proofs of universality random metrics theory. In the dynamical picture by Oerter, Xiao, Schlein, knows all these collaborators around this group in order to arrive to the universality in the random metrics. So basically, universality is I'm trying to simplify a bit the statement, is a technical statement, but the idea is that the details of the spectrum of these metrics, the behavior of the eigenvalues, do not depend on the choice of the randomness inside, but more on the choice of the symmetry class of the metric. So if you are unitary or this type of symmetry class matrix, is like a universality. The randomness in the when n, the size of the matrix is larger and larger, starts to dissipate essentially. And they use this type of technique in order to show this type of results. They use this type of Dyson Brownian motion because it appears as the eigenvalue process in the random metrics pictures that they want. This Dyson Brownian motion has a very fast convergence to local equilibrium. What does it mean, local equilibrium? It means that, okay, this is as you can see, there are some electrons in a heat bath. They take order 1 time to reach global equilibrium. I mean, if you start them from somewhere nice, they will take some order 1 time to really reach the equilibrium. However, there is a notion of local equilibrium. It means that if you zoom in at scales that are up to some n to the epsilon eigenvalues, if you zoom in the spectrum up to n to some, if you see some n to the epsilon eigenvalues inside this band, then you can see the pattern there much faster, essentially in time 1 over n, roughly. So the convergence in the local scale is much faster than the global picture. This is one of the ideas behind this very fast convergence. If you want an intuitive way to think about it, is like this has a nice feature that the local information, that the information is lost very fast in this process. This is actually the link with random metrics. I also mentioned here Professor Johansson from KTH. I think one of the first works in order to prove universality, basically perturbing a Wigner matrix that is essentially a random matrix with entries that are from certain randomness, not necessarily Gaussian, by a Gaussian component in order to see this universality. This is a bit on the random matrix part. Now, what is one way to, I'm going to tell you in the last minutes, I think I have 10 minutes, is it correct?
More if you want.
Okay, I'm trying my best to keep it to 45 as in the scale. Okay. So what is the main feature now? So I'm trying, we did a result, so with Kyle and with Andrew, that are some random metrics people, to show the convergence of this type of maps as n goes to infinity. Now, of course, GT infinity, I can tell you from the beginning, is not really is not so physical object because it's saying the number of curves growing to infinity. That's not really realistic. However, we have a good mathematical control on this object. This is why we did this type of application first. What I'm going to tell you from now on is this toolbox between random metrics and SLE. This works also for fixed n. So we are just in the very beginning of really trying to prove things, and the fixed n part is still available. We just did an application that is less physical for now, just to see it at play a bit. So what is this showing is a certain type of convergence, a rate of convergence in this Carapiotri sense for these maps. Again, it's kind of telling you, if I take n to infinity, what's the real control between this type of maps? And you can get this type of result with overwhelming probability in this sense, that the events are happening with this type of control, let's say. So it's a way to say what's happening with n goes to infinity as an application of this toolbox. But this toolbox is going to be more general, and I'm going to come back to this. So first of all, you might ask yourself, what do I mean by GT infinity to start with? So GTN is clear. GTN was the definition, was the family of conformal maps satisfying this differential equation with the Dyson Brownian motion as a driver. But what do I mean by GT infinity now? GT infinity is defined as the following dynamics. Is given by this type of linear differential equation, but with this type of right-hand side that is given by this complex Burger's equation. I guess for people that are familiar with the random metrics, you will see, you probably expected that because in the, it's like a time evolution of a semicircle law at the level of the drivers that should correspond to this type of dynamics. So it's basically, this is, if you want, this is the limiting, this is what we understand by GT infinity, where the right-hand side satisfies these complex Burgers. And you will spot, now let me explain a bit how this toolbox works by the application. So, first thing is that I'm looking at the right-hand side of my Loewner differential equation. So this is now the crucial point of how things work. And this is why we'll see that this is much more general than this application. So I'm gonna write it first here so that you see it better. Let me put a bullet here. So this is my multiple Loewner differential equation that I described to you. So this is my multiple Loewner differential equation. And what I'm saying here, I'm gonna put a black dot here. And I'm gonna call this right-hand side, I'm gonna call this MTN of the following dot. So this right-hand side is MTN. This is the right-hand side of my multiple Loewner differential equation, okay? This is MTN of the dot I evaluated this point. Then what I'm doing next is that I'm considering a time partition. I'm considering a time partition in which I'm going to control this object. So let me draw this picture for you. I'm considering a time partition. I have 0 up to 1, and I'm doing 1 over n. Still, this is like 1 over a little n. This is the partition of time. You can see that the scale is 1 over little n. And now I want to control this type of object. Is the supreme between MT infinity, the corresponding right-hand side of the Loewner equation before integration, evaluates the dot minus MTN. This is my object to control. And I'm splitting this into 3 parts. MT infinity, you see here I have infinity in both, but I have different times. So I'm looking, let's say this is time 1. I'm looking at the time t between time 1 and time 2 in my grid. So I'm looking at controlling this at 2 times, MT and MT1. What is the difference between that? The next part is MT1 with a fixed time, so it's everybody's here now, at this slice of time, but is the difference between n and infinity. And this is MT1 and MT, but with fixed n. And you will see now that these are simple. The first and the third term are simple. Why is that? Because the first term is basically a regularity in time of this type of equation. It's a regularity in time of the equation, right? This comes from the real format of the complex Burgers. And this is the regularity of the Dyson Brownian motion, because this is still fixed n principle. This comes from the regularity. You can control this by the n Brownian motion, Dyson Brownian motion particles. They have 1/2 minus epsilon regularity, and this is done already in the literature. And you can control this term with that type of Dyson Brownian motion really regularity. So this and this are nuts. You can control them for the regularity of the corresponding equations. The middle term, though, is complicated. It's a term that is at time 1, but is to do with n versus infinity. And this is the picture of the random matrices, actually. This is where you can use the random matrix machinery. Because you have n going to infinity. This is exactly the ensemble going to infinity. And this is why this is the useful picture in the random matrix part. So what is the real machinery? So I just fixed beta equal to 1, beta equal to 2 is the same. So I have MTN. MTN, I remind you, is this term. So this is what I call MTN. You realize now that MTN is a if you think about it carefully, you can think about it as a Stieltjes transform. This is something to do with random matrices now. So a Stieltjes transform is usually given by this type of machinery, mu dx over, I hope is made with a minus, I'm going to put it to z minus x there. You'll see that this is actually, if you look carefully on the right-hand side at the MPN here, this is a Stieltjes transform, but for this new measure, a discrete measure. So this is an integral usually. This is an integral over r of mu dx, z minus x. But now I have, if I put here mu to be a discrete measure of this form, that it really gives values only like delta when I hit the random eigenvalues, I'm going to get very close up to some factors to this term here. You see, so it's basically, you can think about this as a Stieltjes transform corresponding to a discrete measure that is really putting mass on the eigenvalues now. And when you see that, you realize that, well, up to some constant, this Stieltjes transform, people in random metrics like to use this type of identity between the Stieltjes transform and the normalized trace of a resolvent of a matrix. So what is the main idea? Now you recover the right-hand side of the Loewner equation as a random matrix object. This is a normalized trace of a random matrix. So you started with MTN, that was your right-hand side of the Loewner, and this is now a normalized trace of a random matrix, of a resolvent of a matrix. AT is simply square root of T, time factor, times A, where A is a GOE. What is a GOE? GOE is a Gaussian orthogonal ensemble. You can think about it as a matrix of this form. So I have square root of two normal 0, 1s on the diagonal. And I have the entries here, of course, are equal to the entries there, and they are all normal 0, 1s. Okay? So basically, I have this type of Gaussian ensemble, and I factor it with the time of, I multiply with the square root of t, and I take the trace of the inverse of this type of object, and this is the normalized trace of this random object, of this random matrix. Now, once you get this idea that the right-hand side of the Loewner can be seen as a random matrix object, you can start to use the random matrix machinery. So I'm going to be very brief. I have just 2 slides now. Now, the MT infinity satisfies what is called a self-consistent equation. You can think about it that MT infinity, if I would really have n going to infinity, this normalized trace of a resolvent satisfies a nice equation, while the fixed n version almost satisfies it. So it's very close to that in some sense. So it's like you have some bounds on how MTN satisfies this type of equations, almost equal here. And this is helping you to control this difference at a fixed time between MTN and MT infinity. MT infinity will have nice formulas. MTN is very close to that by random matrix estimates. So essentially, you have a way to say that at each slice of time, because this is a fixed time object, at each slice of this time grid, I have a good control on this type of difference between MT and MT infinity. You can see that here. It's enough in order to get a uniform bound on these differences that I can then I can just control everywhere. You know, it's basically, this idea is that at each slice of time, you can use random matrices and then move between the times with uniform bounds and regularity of the Dyson Brownian motion between that. And this works also for fixed n. And this allows you to control essentially the dynamics of these maps. It's a bit more complicated than that, but this is the main idea. If you want, I can tell you more on this. So coming from a Loewner theory perspective and recovering the right-hand side as a random matrix perspective gives you some tools for each slice of time to analyze and moving between these points. And so summary of the toolbox, this is really my last slide, is, well, I started just to recap again what is the main point of this talk in the end of the day. This is a beginning of a story. If you want a startup, we try to push more of these results in the future. This is the first application. You start with the multiple Loewner differential equation. That is a generalization of the first one. And really the Brownian motion is the Dyson Brownian motion here. And you look at this right-hand side and you write it as this type of object, in which I put here the dot as the putting this variable. You recognize that this is a Stieltjes transform for a given choice of measure. And now once you realize this, you realize that for beta 1 and 2, you have a nice way to write the Stieltjes transform as a normalized trace of a random matrix. So you basically started with a Loewner, with an SLE object, and you see it before integration as a random matrix object, and it gives you access to all these tools. And basically, the main idea why I think it's a good idea to push in these directions is that the critical parameters, kappa 4 and 8, correspond to the nice beta 1 and 2, the GOE, GOE parameters in the random matrix literature. There is a lot of literature on those, also more general beta literature and so on. So it's a lot to be done. Also in the future, I had here some thoughts what one can try and so on, but I think I should stop now and wait for your questions. So thank you very much for your attention.
A lot questions?
There's also beta equal 4. But
Yeah.
you're learning matrix.
Yeah, you're absolutely right. So beta equal to 4 will be the kappa equal to 2. It will be the quaternion version of that. I was a bit too afraid to go into that, but you are absolutely right. So beta equal to 4 is another, it's another nice case from the random matrix viewpoint that will correspond to kappa equal to 2, the multiple loop erase random walk. It's a very good point, yes. Yes.
Is there a completed object for all time?
Yeah, that's a good point. I think it's more like, could be possibly merged together, but I think for now it's more like a fixed slice of time. This is most of the literature in random matrix literature that I read about. The people look at a fixed slice of time because they really care about this statistics there, kind of. I'm sure there should be some other objects, but that is not clear to me now. Probably it's a very good point, actually. Yes, it should be some composition of those. Yes. Any other?
More questions? Okay. Sorry. Yes, I don't know if no question. Okay.
Okay.
Thank you very much.
Sure.
So let's thank again our speaker.